Hello and welcome to my video blog. Today we're going to use the E6B to calculate some basic flight calculations you would probably see on either your FAA written or during a flight instructor's flight review or ground test. We will go through ground speed, time, distance, OAT, pressure, altitude, indicated airspeed, calibrated airspeed, true airspeed, density, altitude. That's just the basic calculations that are on the front of the E6B. I like this one. This is an older one. I think I got this one about 1989, first time I went to ground school. Ground speed, you see on the outside of the E6B, you have all these numbers that are graduated in different marks. They're not the same. Yeah, if you notice, the graduation marks are not the same everywhere, but the inner and the outer wheel actually match themselves. If you line these up, even though the graduation marks are different, they are the same, inner and outer, if you line them up with the numbers the same. But outside is the distance. For our purposes, for these examples, with the outside of the disc. For the E6B, these numbers along the outside edge are going to be distances. The numbers on the inside are going to be times. Minutes, depending on how you're using the E6B, the minutes on this ring, the inner ring, will be hours. If you use 3600 as a rate instead of 60, this could be minutes and seconds. And there's two rate marks on here. You have a 60. Normally most calculations you're going to use 60 as a rate for calculating. You use 60 minutes or an hour, 60 seconds or in a minute. But 36, there's another time mark at 36. Actually 3600, but you can use multiples of these numbers. Add zeros, subtract zeros. Moving decimal places, you can do that for pretty much any of these. Yeah, here, at 36, you have a second mark right here, and you sit and you think, well, why would you want a second mark at 36? 60 times 60 is 3,600. There's 3,600 seconds in an hour. So if you're doing a calculation for a really small distance, really small times where you want something in minutes and seconds and you want it to be accurate, you could use 36 as a rate, which is not something many people think about actually. 60. So I've made up a couple practice examples for me to test myself. Some of these were pulled out of FAA tests that I looked over recently, but distance, time, rate on the inner side of the wheel. So if you line up the 60 with a rate, a distance on the outside will match with a time on the inside of the wheel. So say if you have a ground speed of 180, okay, this doesn't go to 180, so you just drop a decimal place. So 180 would be 18. Yeah, if you're going at a ground speed of 180 knots and you go a distance of 300 nautical miles, how much time has elapsed? It's just a very basic problem. So try moving this to 180. There's 180, then we'll look for 300. That would be 30 because there's no 300. 30, you look to the inside of here and you have 10. And then drop down and you see to the inside of here that'd be an hour and 40 minutes. So it would take you approximately an hour and 40 minutes to go 300 nautical miles if you're going 180 knots. Now, let's do another one where we're trying to find distance. For this problem, you're going at a ground speed of 126 knots for 43 minutes. How far do you go? And you want this number in nautical miles. You don't want it in statutory miles. Nautical miles. So I will move our rate arrow to at 126 knots, that would be 12.6. So at 126 knots for 43 minutes, here's on our minute scale to the inside 40, 1, 2, 3 lines up with about 87, it looks like, about 87. You would go about 87 nautical miles in 43 minutes if you're traveling at the ground speed of 127 knots. So we'll do another example where we're trying to find ground speed. So if you cover a distance of 15 nautical miles in a time frame of 8 minutes, what is your ground speed? In this case, you would line up 8 or 80 on the inner ring with a distance, which would be 15. So line up 80 with 15. And if you notice, the units on the inner and outer ring are different, so you just have to use a little bit of common sense. So look to your rate. Your rate arrow at 60 is going to point, it looks at about 11.3. So that's needs one decimal place, so you'd say 113 instead of 11.3. So at a ground speed of 113 knots, you should cover 15 nautical miles in 8 minutes. Sounds about right. Now we're going to look to the interior windows of this flight computer. You notice there's several windows here. You have a density altitude window. You have another window over here for pressure, altitude, and for OAT, the outside air temperature. And you align your temperatures and your pressure altitudes to look to the center window to get a density altitude. And normally a pressure altitude is the altitude that the altimeter would indicate if you were to move the atmospheric pressure to standard conditions, which normal standard conditions would be 15 degrees Celsius and 29.92 inches of mercury. Yeah, so you'd obviously set your altimeter back to what it was to begin with, but you'd set your altimeter to 29.92, get the reading off of the front of your altimeter. That would be your pressure altitude. And yeah, in this example we're going to use here, that's halfway to what we're looking for. So if they give you something like, in this example, you have an OAT of minus 20 degrees Celsius, pressure altitude of 10,000 feet, and an indicated or calibrated airspeed of 150 knots. For our purposes, indicated airspeed and calibrated airspeed are roughly the same, so we're going to treat them the same. So we'll look to the inside of this window and find minus 20. These tick marks, this outside white numbers on the right-hand window of this E6B, these tick marks, these are in 5 degrees of Celsius. Each tick mark, so 20. Yeah, it's hard to, they're really tiny, you have to look really close. So you have 20 here on the inside, and you want pressure altitude of 10,000 feet. You want to line up minus 20 degrees Celsius with 10,000 feet. Once they're lined up, on the inside of the window you can read density altitude, and these numbers are in thousands of feet. So it's like about 7 or 8, 8,000 feet. Density altitude is 8,000 feet when you have an OAT of minus 20 and a pressure altitude of 10,000. And the other part of the question is the true airspeed. How do you get the true airspeed if you're giving an indicated or calibrated airspeed of 150 knots? Well, if you look on the outside of here, in these small, you see that TAS? It's on the outside of the ring. You see a CAS that's on the inside of the ring. So we're looking for the true airspeed. So if you follow 150 on the inner ring, that would be 15. And opposite of 15 is a little bit, about 17. That'd be about 170. About 170 knots true airspeed, given a density altitude of 8,000 feet, indicated airspeed of 150 feet, pressure altitude of 10,000, and OAT of -20. We'll do one other variation of that. This next problem we're going to have, I'm going to try this at, if you're ever given a pressure altitude of 4,500 feet, OAT of 10 degrees Celsius, you don't know the density altitude, you don't know the calibrated airspeed, but you're given true airspeed of 150 knots. Say you're going from point A to point B, and you want to maintain a given altitude and a given speed so you can arrive in a given time. So given that altitude and given that speed, what does your indicated airspeed need to be? Or calibrated airspeed, which for our purposes they're going to be about the same thing. So first thing we need to do is figure out what the density altitude is. So pressure altitude, if we were in an airplane, we'd set the altimeter to 29.92, take a reading. Use that reading in thousands of feet on the inside of this window. We're given, in this problem, we're just given the number 4,500 and an outdoor air temperature of 10 degrees Celsius. So we line up 10 degrees Celsius with 4,000. Oh, that's really moving it. They're given in thousands. $4,500. 10 degrees Celsius. I'm looking at the wrong window. Yes, 10 degrees Celsius and 4,500 feet. Look to the inside window. We have a density altitude of approximately 5,000. Pressure altitude 4,500, density altitude 5,000 feet. Okay, calibrated airspeed. That would be on the inside of the circle, so in this example it's going to be backwards. We want a true airspeed of 150 knots. We go to 15, look to the inside. Calibrated or indicated airspeed is a little bit less than 140. So I'm going to say 139. 139 knots. Calibrated airspeed. Okay, these are the first examples for the use of the ASA E6B. You can do the same calculations on a CX2, which I found this one to be a lot easier, a lot faster, a lot more practical. But E6, on a flight examiner review, they may want to make sure you can use the E6B, even though it's outdated, it still has practical use. I guess the batteries never die. But we will save that for another time. Flight. Okay, that's it for the E6B. I hope you enjoyed this video, and I hope you learned something.